Very good morning, student. Today's topic is program and network properties. So the table of contents are like this. So in this video lecture, we'll see the conditions of parallelism. Then we'll see the problem of partitioning and scheduling. Then the program flow mechanisms. Then system interconnect architectures. So in this video lecture, we'll see the conditions of parallelisms. So first we'll see the data dependency. So the ordering relationship between the statements is indicated by the data dependency. So there are 5 types of data dependency as shown below. So the first one is the flow dependency. Statement called S2 is a flow dependent on a statement S1 if an execution path exists from S1 to S2, and if at least one output of S1 feeds in as an input to S2, then it is a flow dependency and it is indicated or denoted by the S1 arrow mark S2. So this shows the flow dependency. That is, the statement S2 is a flow dependency on statement S1. So we'll see later the examples, how the flow dependency is shown with the examples. So next one is the antidependence. So this antidependence can be defined as, if suppose the statement S2 is an antidependent on statement S1, if S2 follows S1 in program order, and if the output of S2 overlaps with the input of S1, then it is an anti-dependent. And a direct arrow crossed with a bar as in S1 to S2 indicates the anti-dependent from S1 to S2, as you can see in this figure. The next one is the output dependence. Two statements are output dependent if they produce the same output variables. Then those two statements are the output dependence because they produce the same output. So hence the S1 and S2 are called as the output dependence. Then comes the input output dependence. So the read and write operations are the IO statements. So the IO dependence occurs not because the same variables are involved, but because the same file is referred by both IO statements, like the read and write statements refers the same file. Then those dependency is called as a input output dependency. Then the last one is the unknown dependence. So the dependence relationship between the two statements S1 and S2 cannot be determined in the following situation. If the subscript of a variable as itself subscribed, that is indirect addressing, then it will be a unknown dependency. Then the subscript does not contain the loop index variable, then it is an unknown dependence. And a variable appears more than once with the subscripts having a different coefficients of the loop variable. Then the fourth statement, that is the subscript is non-linear in the loop index variable. Then with these conditions, so the dependency is called as the unknown dependency. Now we'll try to understand the dependency with the example. So that is a data dependency in a program. So consider the following code fragment of 4 instruction. So statement 1. So what it indicates, load R1 comma A. So we are loading the content of A. So A indicates here memory. So we are going to load the content of memory onto the register R1. So whatever the data is stored into this memory location, So that data is moved into the register R1. So this is what the statement 1. Then statement 2, add R2 comma R1. So this assembly level language statement so performs the addition of R1 and R2. So perform the addition of R1 and R2 and store the result into the R2 here. This is statement 2. Then statement 3. So we are moving the content of R3 into the R1. Then statement 4. So we are storing the R1 value onto the memory location here. Okay. So B is in a memory location. So whatever the value is stored into the R1 is moved or stored onto the memory location called B here. So in this statements, as you can see, statement 1, statement 2, statement 3, and statement 4. So S2. So S2 is a flow dependent on S1, right? So S2 is a flow dependent on S1 because the variable A or the memory location A is passed via the register R1. So hence S2 is a the flow dependent on S1, and S3 is anti-dependent on S2. S3 is anti-dependent on S2 because of the potential conflicts in a register contained in R1, right? As you can see, so R1 register is used here as well as the R1 registers are used. So hence S3 is anti-dependent on the S2 here, right? And the statements S1 and S4 are independent. So they are not dependent on any of the statements, right? So those statements are called as what? The independent statements. Now you can see the diagram, that is a dependence graph. So we can plot the graph as the S2. So this S2 is the flow dependent on S1 and S3 is the anti-dependent on S2, right? So this is the flow dependency and this is the anti-dependency statement, so which is indicated with this type of an arrow here. And S1 and S4 are independent, so they are not dependent on the other statements, so they can be executed independently. So hence, so those statements are called as what? The independent statements, because they are not dependent on the other statements here. Next, we'll consider a code fragment involving the input-output dependency. So in the previous example, we have seen the flow dependency and anti-dependent statements. So in this example, we'll see the input-output operations here. So as shown in this figure, so S3 is input-output and dependent on S1, right? So how? So S1 statement is what? We are going to read array A. So this is array A from the unit 4. So we are going to read the A of fourth element. Getting my point? So we are going to read the A of fourth element. Then S2 statement rewind the content of A of 4. Then S3 is write array B onto the tape unit 4 here. So B of 4. Then rewind. So so here the statement S3. Okay, so we are going to write the value of array of B into the tape unit 4. So the read write statements S1 and S3 are IO dependent on each other because they both access the same file. Okay, so they access the same file. So the above, the data dependency relationship should not be violated during the program executions. So these two statements which are IO dependency, so which uses the same file, so which is indicated in this diagram here. Why they are input output dependency? Because we are reading and writing the operation with the only one file, so both uses the same file. So hence to execute these two instructions we require the file, and both are dependent each others. Now coming to the control dependency, so this refers the situation where the order of execution of statements cannot be determined before the runtime. For example, if statements. So these statements is a situation where the order of execution of statements cannot be determined. Right? It all depend upon the conditions, what conditions we are putting into the if conditions, right? So in this type of conditional statements, it can take the different path after a conditional branch may introduce or eliminate the data dependency among the instructions. Dependence may also exist between operations performed in successive iterations of a looping procedures. So here we can see one example. So this the first example shows the successive iterations of the following loop are control independent. So these are what the control independent statements. How we'll see. So in this example, we have used a conditional statement that is if. Okay, so I'm going to assign I is equal to 1 here. So one value is assigned to I value. Okay, and then A of I, that is A of 1, is equal to C of 1. If A of 1 less than 0, okay, then what we are doing, we are performing A of I is equal to 1. So this conditional statement which is of a control independent. Then the second example we can see that so these statements are the control dependent iterations. How we'll see, if I is equal to 1, okay, then if A of I minus 1, so that is 1 minus 1, then it will become as A of 0 equal to 0. Okay, I'm checking the conditions here. So I minus 1, that is A of 0 equal to 0. Then I am performing A of I is equal to 0, so which is control dependent iterations, right? So it depends upon the value of I, then A of 0, right? So in the first example we can see this is the successive iterations, right? So the value or the index will not change here, so it remains the constant, but here the index is changed, like A of I. In first example we have seen I is equal to 1, but here the index is changed to 0 here, right? So hence we can see it as what the control dependent iterations, right? And control dependency often prohibits the parallelism from being exploited. So the compiler techniques or hardware branch predictions techniques are needed to get around the control dependency in order to exploit more parallelisms here. Now going to the resource dependence. So this is different from the data or control dependence. so which demands the independent of the work to be done here. So resource dependency is concerned with the conflicts in using the shared resources. If the two statements which are shared the resources, then it will become as a what the resource dependence. So such as integer units, floating point units, registers or memory areas among the parallel events, right? So if the conflicts involve in these storage, we call it as a storage dependence. Then the conflicts can be occurred in arithmetic logical unit. So we'll call it as a what? The ALU dependence. In case of storage dependence, each task must work on independent storage locations or to use the protected access. Right? The detection of parallelism in programs requires a check of the various dependency relations here. Now going to the Bernstein's conditions. So what is this Bernstein conditions? In the year 1966, Bernstein revealed a set of conditions based on which the two processes can execute in parallel. A process is a software entity corresponding to the abstraction of the program. And here we define the input set I of a process, P as a set of all input variables needed to execute the process. So I indicates input, P indicates the process as a set of all the input variables which are needed to execute the process here. Similarly, the output set O consisting of all output variables generated after execution of the process P. Now consider the two processes P1 and P2 with their input I1 and I2 and the output O1 and O2 respectively. These two processes can execute in parallel and which is denoted by P1 parallel to P2, right? So here we are considering the two processes so which are executing parallelly here. So hence we can indicate the two processes with this symbol here, P1 parallel P2, if they are independent and therefore create a deterministic results here. So formally these conditions are stated as follows with this symbol: I inputs and O indicates outputs. So these three conditions are known as Bernstein's condition. The input set I is also called the read set. Then similarly the output set O has been called the write set. Okay, so I is the input set and O is the write set, and the range of a process P. So in terms of data dependencies, the Bernstein condition simply imply that two processes can execute in parallel if they are flow independent, anti-independent and output independent here. And the parallel execution of such two processes produces the same results regardless of whatever they execute sequentially in any order or in parallel here. So this is because the output of one process will not be used as an input to the other process. Okay. Now we'll consider an example. In this example, we are going to determine the parallelism embedded in the following statements, and we are going to draw the dependency graphs here. Okay. So in this example, the process P1 which performs the multiplication between D and D and stores the result into the CL. So C is equal to D into E. Then process 2 performs addition between G plus C and the value is stored into what? EM here. Then P3 B plus C, then on to the A. L plus N, that is the process of 4, then stored into value. Then 5 C plus C and value stored into the F here. Now we'll see the data dependency graph. Okay, so as in this figure we can see this is the data dependency graph. Okay, showing both data dependency and as well as the resource dependency. So data dependency, which are shown as the solid arrows. Okay, then the resource dependency, which is showed as the dashed arrows. And here I apologize for you people for the poor quality of the image. Okay, so here I'll indicate the dotted lines here. Kindly excuse the image quality of this presentation. So this is all what the dotted lines indicates the resource dependency, and the solid lines, and this is solid line, shows the data dependency here. Okay, so for example, if I consider P2, right, so P2 is only the flow dependency onto the process P1. How? Because if I want to calculate the value of M, I am performing the addition between G plus C, right? So to get the value of C, so first process 1 should be executed here. Hence, a P2 is a flow dependent on P1 here. Got my point? Then P2 and P3. So P3 is a flow dependency on a P1. Why? Because P3 consisting of the statements like A is equal to B plus C, right? So to get the C value, so first process 1 has to be executed here, right? Then only I can get the value of A, because A is equal to B plus C, and process 1, that is C is equal to D into E. Then performing the multiplication between D and E, I'll get the value of C here, right? So that value is used into the process 3 here. So hence process 3 is a flow dependency on P1 here. It is a flow dependency. Okay. Then process 4. Process 4. So what kind of a dependency it is? It is a dependency of output dependency here, right? So P4 consisting of the statement C is equal to L plus M, right? C is a part of what? P1. Got my point, right? So hence to get the output of C, so P4 is the output dependency on P1 here, right? So this is what the output dependency, that is 4 is the output dependency on P1 here. If I consider P5, can you identify any dependency on P1, P2, P3, P4? No, right? P5 is independent. So G plus E. So G not dependent. E is not dependent on any process. So hence it is a independent process here, right? And dotted lines which indicates the resource dependency here. P4 is a resource dependency on P2, right? Because M, which is used in a P4 statement, right? So to get the M value, so we need to depend, or process 4 need to depend on the process 2, which is of a resources, because the resources is shared from the process 2 to the process 4 here, right? So this is what the data dependency graph showing the both data dependency and resource dependency here. Now we'll see execution of these statements. Okay, so two types. One, these statements can be executed sequentially, one by one. Then they can be executed parallelly, right? So this B figure which shows the sequential execution in 5 steps, right? So it consisting of 5 processes here, P1 to P5, right? Then they can be executed sequentially, assuming 1 step per statement here, no pipelining. So here no pipelining, That means there is no parallelism involved in the first execution and the second one. So this is what the parallel execution here. Okay, so we'll see that is first process 1 is executed. So to execute the process 1 we require what, d value and e value. So those values are supplied here. So d value and e value is supplied to the process 1. Then what is the output? I'll get the c as the output here. So that will be the input to the process 2, right? Because m is equal to g plus c. As you can see here, m is equal to g plus c. All right. Then to execute the process 2, that is m is equal to g plus c. So we require the output of p1, that is c, and the value of g. Then I'll get the output of m, that is m value. So that will be supplied to what? Again to the process 4. So process 4, c is equal to l plus m. So here you can see here. So m, so which is dependent on the process 2, the resource dependence. This is called what? The resource dependence on p2 here, right? Then p3. So p3, that is a is equal to b plus c. Then b value is supplied, and c value, that is the from the process 1. So c value it gets. Okay, so sequentially in this example, each statements are executed one after the other. So hence it is a sequential execution here. Then in the second diagram, so this is parallel execution here. Okay, so this is one process I'll take, and this is another process. Okay, because p1, p2, p3, p4 are dependents in one another way. So they may be the data dependency or the resource dependency, as we have seen in last example. So p1, p2, p3, p4, this is all what they are dependents among each other. So hence we will take those processes, and those processes will be executed in one cycle, and another process, that is p5, which is independent, so it will be executed with another execution steps here, right? So here you can see here p1. So by supplying the value of d and e, I'll get a c, right? And so this c is dependent on or p3 and p2 are dependent on the c value. Okay, and p4, which is dependent on the p2 here, right? So p2, p3, p4, they are dependent on the one another, and these four processes are executed in one step, and the another process, that is a p5. So that is which is independent of the remaining process. So it will be executed separately here. Okay. Thank you for watching this video.